Welcome to Fluid Mechanics N6. Today's presentation is going to be on reciprocating pumps. This is part of the module on pumps. We have reciprocating pumps and we also have centrifugal pumps. For this video, we are only focusing on reciprocating pumps. There is another video on centrifugal pumps. Let's begin. The verb to reciprocate simply means to move back and forth continually, okay? So if you have something that is moving back and forth, back and forth, back and forth, or maybe up and down, or maybe from right to left, then that thing will be said to be reciprocating. And so in a reciprocating pump, we use the term reciprocating pump because you have a piston inside of the cylinder that is moving back and forth, okay? And so there are two main types of reciprocating pumps we're going to study. The first one is the single acting reciprocating pump, and that is a figure for it here. And as you can see, you have water inside of a sump, and the purpose of a pump is to be able to take this water from the sump and to deliver it to a desired place, okay? It could be a unit, a house, or maybe some other tank, some other reservoir. And so what the pump does is that it can draw water from the sump, or maybe it can be a tank or a well, and it will deliver that water to a desired place, okay? And so the way it works is that initially this piston that you see here will be on the far left, and then as the piston begins to move to the right, the suction valve is going to open, and as this piston is moving to the right, it will suck in water from the sump, okay? And this water will come inside of the cylinder and it will fill the chamber of the cylinder. Once the piston reaches the far right, the suction valve is going to close and the delivery valve is going to open. And as the piston is now moving from right back to the left, it will then push out the water that was inside of the cylinder's chamber, and that water will then be delivered through the delivery pipe because the delivery valve will now be opened. Okay, and so that is pretty much how a single acting reciprocating pump works. And once you reach the left and all that water has been delivered, the delivery valve will again close and the suction valve will open again, and the process will repeat itself. Okay, so what is important to see here is that the piston is of course connected to a piston rod, and this piston rod is connected to a crank by means of a connecting rod. And now the crank here rotates, okay? We will assume for this example that it is rotating clockwise. So as you can see, the crank is going on a circular path. But although the crank is going on a circular path, the piston here is only allowed to move horizontally, okay? So it is constrained to move horizontally. So when the crank is at point A, going on its circular path until it reaches point C, the piston here, when the crank is at point A, the piston will be on the far left. I hope you can see that. And as the crank moves to reach point C, the piston will be pulled to the far right, okay? Because as you can see, point C is the point that is the farthest to the right. And so as the crank moves now from C back to A going through D, okay, the piston will now move from the far right back to the left, okay? That is what will happen. And so you can see therefore that as the crank goes around like this, the piston will move from left to right and then right back to left, okay? So that is what one full revolution of the crank will do to the piston, okay? You can think of it. If you are here at point A with the crank and you go to a full revolution back to A, the piston when the crank is at A will be on the far left, and then it will reach the far right when you are at C, and from C back to A, it will again go back to the left, okay? So one full revolution of the crank corresponds to a motion of the piston from left to right and then right back to left. Now the angle here is the angular displacement of the crank, okay, theta. Theta is referred to as the angular displacement of the crank. And you can see when the crank is at A, okay, the piston, as I said, is on the far left. By the time the crank reaches point C on its circular path, okay, the piston will be on the far right. So you can see that as the crank moves from A to C, the piston will move horizontally through its stroke length, okay? So it will move from the far left to the far right. So it will be one stroke length as the crank moves from A to C. And because the piston is constrained to move horizontally only, so as the crank moves from A to C, the piston will travel inside of the cylinder a distance that is equal to the distance between A and C, this horizontal distance, because the piston can only travel horizontally. And because now that distance inside of the piston, inside of the cylinder, through which the piston travels, that distance is the stroke length as the crank goes from A to C. Therefore, you can say also here, this horizontal distance from A to C is the stroke length, okay? That is what it is. So the distance between A and C, this horizontal distance, AC, is the stroke length. And of course, it's equal to twice the radius of the circle along which the crank is moving, okay? Twice the radius of that circle is the stroke length. Okay, I hope this is making sense. And so theta, as I said, is the angular displacement of the crank. So theta is 0 when the crank is at A, and 90 when the crank is at B, 180 when it is at C, and so on. And now the acceleration of the piston is going to be maximum when the crank is at A and when the crank is at C, because at A, the piston is just about to be set into motion towards the right, and therefore it must have its maximum acceleration at A, okay? And then at C also, when the crank is at C, the piston will be on the far right. And on the far right, it's about to be set into motion towards the left, okay? And so it will again have its maximum acceleration when the crank is at C, or when the piston is on the far right. So maximum acceleration is when theta is equal to 0 and when theta is equal to 180, okay? And although these accelerations are maximum and they have the same magnitude, but they will have opposite directions, because when the crank is at A, the piston is about to accelerate to the right, but when the crank is at C, the piston is about to accelerate to the left, okay? So opposite directions for these accelerations, but same magnitude, and there are maximum accelerations here and also here, okay? Very important. Now, the velocity will be maximum when theta is 90 degrees, because the acceleration here will begin as a maximum when we just begin to move towards the right. But when we reach the middle of the stroke, we have to start decelerating, because this piston must come to rest on the far right here, okay? So we only accelerate until the middle of the stroke, and from then, that's when we reach maximum velocity, and we have to begin to decelerate, because the piston must come to a stop on the far right, because it is supposed to now move in the other direction. So the maximum velocity is achieved in the middle of the stroke, or when theta is equal to 90 degrees. So remember, maximum acceleration is when theta for the crank is 0 and theta is 180, and maximum velocity is when theta is 90 degrees, because the maximum velocity occurs in the middle of the stroke. And so the height from the level of the water in the sump or the tank, whatever reservoir you have, the level of the water, the distance from the level of the water from the sump to the cylinder is called HS, and that is the suction head. And the distance from the cylinder to the level where we want to deliver the water is called HD, and that is the delivery head. So from the sump to the cylinder is the suction head, from the cylinder to the delivery place is the delivery head, and the sum of the two will be that length, and that is what we refer to as the static head, capital HS, okay, static head. Very important. So L is the stroke length, as I explained, okay. HS is the suction head, small hd, delivery head, capital HS, that is the static head, and static head is equal to suction head plus delivery head. Now, the second type of reciprocating pump we're going to look at is the double acting reciprocating pump. And this one here looks like that. And as you can see, you have two suction pipes and you have two delivery pipes. In this case, the water is not only filling this side of the piston, but the water is allowed to fill also this other side of the piston. So this cylinder has therefore two chambers. So as the piston is moving from left to right, in this chamber here, water will be coming in, okay, because the suction valve is going to be open, and then as the piston is moving from left to right, water will fill this chamber. Of course, the delivery valve will be closed. And once you reach the far right, now the suction valve will close and the delivery valve will open. And as the piston begins to move from right back to the left, it will deliver the water that it sucked in previously inside of this chamber. It will deliver it to the delivery pipe. But while it is doing that, on this side now, the suction valve is going to be opened and it will be sucking in water inside of this chamber while delivering the water that it sucked in previously in this chamber as it is moving from right to left. Okay, that's what will happen. On this side, it will be delivering. On this side, it will be taking in the water. When it reaches the far left, okay, the suction valve will close here and the delivery valve will open. So as it moves from left to right, now the water that was inside of this chamber will be delivered, while at the same time as it is moving from left to right, on this side, it will be sucking in water and the delivery valve will be closed. I hope you see how that works. And so you can clearly see that for one revolution of the crank, this double acting pump will deliver twice as much water as a single acting pump. Okay, very, very important. And again, the height from the sump level to the cylinder is the suction head, and the height from the cylinder to the level where we're delivering the pipe is delivering the water, is the delivery head, okay? And the sum of the two, of course, is the static head. And again, a very important note, which is what I explained earlier, that for one revolution of the crank, a single acting pump will deliver a volume of water equal to the stroke volume, okay? But for a double acting pump, the amount of water that will be delivered with one revolution of the crank will be equal to twice the stroke volume of the cylinder, okay? And the reason for that is because it is taking in water on both sides of the piston, okay? So it's got two chambers, so it is able to do twice the work, okay? So I repeat, the volume of water that is delivered with a single acting pump through one revolution of the crank is just equal to the stroke volume of the cylinder. But with a double acting pump through one revolution of the crank, the amount of water that you can deliver is twice the stroke volume of the cylinder. Okay, that is easy to see. If you just look, for instance, at this diagram here, when we are at A, the piston is on the far left. From A to C, the piston will reach the far right when the crank is at C, so it will be the chamber of the cylinder will be full of water because it would have drawn the water as the piston moved from left to right. And then from C back to A, the piston will then move from the far right to back to the left, and therefore pushing the water that it's sucked in, because of course the suction valve will be closed and the delivery valve will be opened, and it will push that water out, okay? And so that water that is being pushed out is the same as the volume inside of the cylinder, the stroke volume, okay? But with a double acting pump, when you go through one revolution, you will push out twice as much water, because from A to C, okay, you can imagine if we had drawn the full thing here, as it moved from A to C, while it is sucking in water in this chamber, in that chamber it will deliver, okay? Whereas with a single acting pump, when it is sucking in water, it is not doing any delivery. Okay, so this one from A to C will already deliver one full stroke volume, okay? And then from C to A, it will again deliver another full stroke volume, okay? So it's twice the stroke volume that will be delivered in terms of the quantity of water delivered, okay? It's going to be twice the stroke volume when you're dealing with a double acting pump. So I hope I am making myself clear and this explanation was useful. And so let us carry on. So now we will speak about some of the faults that you experience when you're dealing with reciprocating pumps. Okay, of course there are many faults, but I am going to speak about three that are, I think, the most important for you to know. The first one is the water hammer. Okay, this basically occurs when a flow of water is brought to a stop suddenly. Okay, so you had water flowing inside of the pipe, and then suddenly you close the valve and the water that was coming is suddenly stopped, and that can cause some shock waves inside of the pipe, and you can have some vibrations. I don't know if you've lived in an old house, but if you have, sometimes the piping is no longer proper, and so whenever you're trying to close the tap, you can find that the pipe is vibrating, and this is usually water hammer, okay? It's caused when the flow of pipe is suddenly closed, and I can illustrate it with this picture. You can see here there is water flowing freely inside of the pipe, and then suddenly the valve is closed, and so because the valve is closed, now some of the water that was coming will bounce off the valve and want to go back in this direction, but only to meet the water that is incoming, and so you will have some sort of a collision of water, okay? And that will cause vibrations and shock waves inside of the pipe, and if it is bad enough, that can even damage the pipe, okay? And so the way to prevent that is to use air vessels, okay? Usually in a pipe assembly you will have air vessels that are installed, and this is to also prevent water hammer. And let us look at this piston here. You can see it is on the far right, so we can assume that right now what it was doing is sucking in water, and so the delivery valve is closed because it's on the far right, so it must have been sucking in water, and now it's about to start moving to the left to deliver the water that it sucked inside of this cylinder. And so for it to do that, first the suction valve must be closed, and then the delivery valve will be opened, okay? And the piston is now moving to the left, okay, to deliver the water that it sucked in, okay? Now, because we just closed this suction valve, of course, you still had water that was coming in, okay? The water didn't know that the suction valve was about to be closed because now it's the delivery phase that's about to start. Okay, so once we close the suction valve, the water that was here and that find the valve suddenly closed will bounce off the valve and begin to move down, okay? But it will go and meet the water that was yet coming up, okay? But now, instead of it colliding brutally here, we have an opening for the air vessel, so the water will just go in that direction, okay? And in the air vessel, there is air, and this air is going to be compressed by the water. and so you will have high pressure inside of the air vessel here. And then, of course, when you will open again the suction valve, because of the high pressure here, it will cause the water to come down again like this. And so the flow can be continuous, and you will prevent water, hammer, and even bubbles inside of the flow. Okay, so that is pretty much what is